Okay, so today we're glad to have Richard Schwartz, and she's going to talk about Thurston
Shapes of Polyhedra.
shapes of Polyhedra.
Right. So okay. So this is a completely an expository talk. There's my only contribution to it was at some point I rewrote Thurston's paper on this because I couldn't understand what Thurston did. So Thurston wrote this paper called originally there was this I guess it's a Annals of Math Studies monograph by Deline and Mostow about some lattices in academic complex hyperbolic space.
No, there was a paper by Mostow before that.
There's a Mostow paper, right. Okay, then there's the Deline Mostow paper, right? There's the 80 paper of Mostow, and then I think I guess it was maybe around 88. I think Thurston wrote this paper called Shapes of Polyhedra, where he gave a more geometric interpretation of these groups, and there was another thing that instead of in complex hyperbolic geometry, there's a simpler thing about polygons that was done in real hyperbolic space. And I mean, I learned this from Thurston, and then I kind of worked out some details myself. And there's a paper I think by Gis and Bavard on this, which apologies to them, I've never actually seen this paper, but anyway. What I thought I would do is I would first explain the Gis and Bavard paper, so shapes of polygons basically, and then I would explain the main ideas in the. What's that?
No, how can you explain a paper you've never seen? What?
I know how it works. No, I thought about it myself, and I know how it works. I mean, you'll see. I mean, it's a simple idea. I learned a little bit.
Something that he believes is in a paper,
Right. So I'm going to explain something. I heard a little bit about this from Thurston, but then I worked out the details. Maybe, but the idea is that it's a little bit hard to think about complex hyperbolic space. It's easier to think about real hyperbolic space first, but somehow there's some fairly direct analogy between the two. And so the plan of the talk is to first explain this thing about polygons, and then to explain the thing about the lattices in complex hyperbolic spaces. So again, I guess this talk kind of fits in some way with my previous talks, and it's about moduli spaces of geometric objects. Okay, so the setup is, let me just concentrate on I wanted to talk about, you have n-gons with fixed directions. Mod translation. So I'm going to take n equals 5 at first, just to draw pictures. And one way to say it is there are kind of two ways to think about it. One way is you think about you just have these 5 vectors that you move in, and then what you're allowed to do is kind of change the shape, but without changing the directions. But I prefer to think of it as that rather than having vectors, you have 5 lines, and what you're allowed to do is to roll the lines around parallel to themselves. I want to say one more thing. My website has these notes on Thurston's paper, so some of this you can read if you want. Anyway, so this is, in this case, this is some. You want to say it's a 5-dimensional vector space, but it's really kind of a 5-dimensional affine space. I mean, because you can just sort of move each line. There's an r's worth for each line. So this thing is R5, although it's a little bit hard to say what the origin is in this space. And then when you mod out by translation, you get a 3-dimensional space, and you could say then what's the origin? It's like say where all the lines go through the same point. That would be the origin. So there's a vector space. There's a vector space of dimension n minus 2. And then there's a function on this space, which is the area function. So by area function, I really mean the signed area. I mean, for example, let me show you the kind of thing you could do. I mean, you could have one of these polygons, and then you could have, this would be a legitimate pentagon. So what you did in this case is you you took for one line that was originally over here, and then you moved it over to here. And so the area in this case would be this region minus the area of this minus the area of that. So there's this area function, and the secret is that in this vector space structure, this area function turns out to be the diagonal part of a quadratic form of signature 1 n minus 3. So I'm going to try to show you that. So the idea is like, let's try to compute the area in some way that reveals what it is. And the way you would do this is you would put local coordinates on this space of polygons, mod translation, and then you would work out what the area was in these local coordinates. And then you would say, oh, it's the diagonal part of a quadratic form. So here's how it goes. I'm not going to do this for all polygons. I'm just going to pick a polygon that looks pretty regular, and then you could say, well, the general thing works by analytic continuation or something, or algebraic continuation. I mean, I don't want to draw these crazy pictures and try to work out the area, so let's just take something which is close to a regular pentagon. Now, there's many coordinate systems you can use, but the point is that the conversions between the coordinate systems, the changes of coordinates, are all linear. So one coordinate system is you can pick your favorite edge, and then you could measure, like you could call this x, and you could call this y, and you could call this z. And you could do this for other choices of edges, and you'd find that the change of coordinates was linear. So what's the area in these coordinates? Well, as you vary these lines around, none of the angles changes, and so the area of a triangle is really some constant times its length squared, where the constant depends on the angles. So the area in this case, well, it's the area of the big triangle minus the area of the two small triangles. So it's like C1 x squared minus C2 y squared minus C3. So there you go. The area is the diagonal part of a quadratic form of type 1, 2. Now, if you did it for a hexagon, you'd have some picture. Well, it's not a hexagon, is it? You'd have some big area minus 3 smaller ones, and so the signature would be of type 1, 3, and so on like that. So the area is the diagonal part of a quadratic form, and of type 1 n. And then if you were to change coordinates, you'd get some different expression for the area, but it would always have the same signature. So you have this quadratic form of type 1 something on this vector space of polygons. So now you can scale. Let's just look at ones with unit area. Well, everybody probably in this crowd knows that the set of vectors of length 1 in this quadratic form is just a hyperbolic space of that dimension. So if you then further restrict to the set of polygons of signed area 1, then this moduli space naturally is it's a hyperbolic space. Yeah, hyperbolic space. Now you might wonder, like, the next thing you could ask is like, well, it turns out there's a group action on this space. Like, you might be interested, for example, what's the moduli space of convex polygons look like? So like, for example, Kurt McMullen told me that somehow he was involved in the beginning of this, and where there was like some question where you have some kind of non-convex polygon, and there were some certain kind of allowable moves that you were allowed to make, and the question was whether you could actually. Kurt said this was a math Olympiad problem related to numbers, but he somehow translated it into This is the history of this. He claims he translated this thing into polygons, and then it eventually came to this. So I want to explain some elementary moves you can make on polygons, and then explain like what's the question you could ask. So the moves are called butterfly moves. So what you do is if you have, and this is the case where it's good to think of these things as lines, because if you have a non-convex polygon, it's hard to see a butterfly move. But anyway, what you do is you've got these lines, and they're cyclically ordered, and you take, say, you take line I, and you have line I minus 1 and line I plus 1, and you see where these two lines intersect, and then you just take I and you roll it parallel to itself until it cuts off the same area that you started with. So this move, I do it for the convex case, but if you just have these 5 cyclically ordered lines, or labeled lines, you could just do this and not worry about the geometry of this thing. You get the geometry of the polygon from the lines by just connecting the successive intersection points. So anyway, if you look at this map, the beauty of this map is that it preserves the signed area, because this area is the same as this. But when you go like this, you're computing it with negative sign. So this is an 8 area preserving map, and moreover, it's a linear map. Okay, so I'm just looking at the picture for the convex case, but by analytic continuation or something, or algebraic continuation, this works general. And so therefore, when you look at how it acts on the unit area polygons, it's a hyperbolic isometry. So the question, somehow this original Math Olympiad question came down to, like, if I'm given an arbitrary n-gon in the plane, or can I make it convex through a series of butterfly moves?
Can you describe the map again as a map?
Yes. I start out with let's say specifically I have a labeled n-gon, and I want to talk about the ith butterfly move. So I pick line I, and I see where line I minus 1 and I plus 1 intersect, and I move line I parallel to itself so that it's the same distance from the intersection point as it was before, but on the other side.
Okay.
And this has nothing to do with the geometry, because you just have to look at the intersection points of these lines. But if you do analyze it for the convex case, you can see that it's both linear and A-preserving. So therefore, just in general, it is. Okay, so let me work out what these things are for the case of, well, let's say regular pentagons. Okay, so, what else can we say about I? So let's give these things a name. We'll call them butterfly 1 up to butterfly n. What can we say about these maps? Well, one thing we can say about them is that they're all involutions. Because if you do it again, you're back. Okay, so that's
So
great.
that's all possible maps, right? So you just choose a pair of edges and you do this.
No, you always, the ith butterfly move involves the previous lines I minus 1, I, and I plus 1. So you could do this for any I, but you're not allowed to choose different edges. I mean, you're not allowed to choose line 9, line 71, and line 403. I mean, you have to do consecutive lines. So, okay, so well, there aren't that many involutions of hyperbolic space. Well, there are, but what can we say about this? Well, this thing has a lot of fixed point sets, because, for example, if your original polygon was like that, where this line went through these points, then that would be a fixed point of this butterfly move. And what's the dimension of the fixed point set? Well, you can vary the other lines freely. So the map has the fixed point set has co-dimension 1. So now we can really say what this butterfly move is. It's a reflection in a hyperplane. Okay, so that's good. Now we've got a reflection group. Let's draw a picture for pentagons. Okay, let me do the regular pentagon first. Okay, so let's look at B1 and B3. B1 and B3 commute. Because if you do B1, this doesn't have to do with it being regular. If you just start out with any convex pentagon and you do B1, and you're just moving these lines independently of each other. So let's call like H, so H1 should be the fixed point set of B1. So, and for 5 points, the dimension of this space is 2, so we're in the hyperbolic plane. So since B1 and what is it? What happens? What's the situation when two hyperbolic reflections commute? The lines have to meet at right angles. The fixed lines have to meet at right angles. That's the only possibility for them to commute. So here's H1. Here's H3. Here's H5. Here's H2. And here's H4. So in this case, you get a right angled pentagon reflection group. And in the case when it's a regular pentagon, just by symmetry, this must be the regular right angled pentagon. But in general, as you vary the directions, that you get different right angled pentagons. And then the convex ones just correspond to this fundamental domain. So the answer to this question, at least for pentagons, is yes, because everybody knows that you have a discrete group, reflection group back in the hyperbolic plane, and you can get anything into the fundamental domain. So in this case, you really can move any polygon to a regular one by butterfly moves, and there's even kind of an algorithm because you can just sort of pick the point you're in and join it by a geodesic to the center, and then just use those reflections. Okay, so anyway, I think that's a beautiful thing. What do you get for hexagons? So for hexagons,
So you can go, what you're saying is that you can take any pentagon and put it back to this fundamental domain.
yeah, right, because we know everything there is to know. Well, we know a lot about that
But
group.
do you have an understanding of this fundamental domain? How does it look like?
Oh yeah. Well, yeah. These are the fixed point sets of these involutions, and what they're the fixed point sets when three lines come to three consecutive lines share a point. So you pick the origin in here, and then as you move around toward the boundary, the boundaries correspond to triples like this, and so. I mean, you have to do a little work to show that the set of convex pentagons is really this and nothing else. But
So you think it is the set of...
it is this. That's right. This is like probably an application of the open mapping theorem or something. So anyway, for any, as long as at least for any pentagon where you can ask like what you get in general for 5 lines, and it depends somewhat on the shape of the pentagon. Like this has the property, this has a property that somehow like you broadly have this picture where each of these lines, like lines 1 and 3, they focus sort of on one particular side of the pentagon. I mean, you can have a regular pentagon that somehow looks like this, where these lines focus on the other side, and then you get something else. But you get a different kind of domain. You might even get something that was non-compact. So let me explain the regular hexagon picture, and then I want to move on to the complex case. So for regular hexagons, you can say all the same words. Now you have you have some kind of group generated by 6 reflections in H3, and there's certainly some commuting going on. Like if you have 1, 2, 3, 4, 5, 6, like B1 and B3 commute, and B1, B3, and B5 all commute. So those, whatever those hyperplanes are, they have to meet mutually in right angles. And then B2, B4, and B6 also commute. So so you've got these 6 hyperplanes, and there's 3 of them meeting at right angles and another 3 meeting at right angles. And then there's a little more structure. Like actually, because you have these parallel lines, the fundamental domain, or the set of convex guys, is non-compact, because you could sort of get something of unit area that looks like this, and as you make this long and thin, you're kind of exiting out of a bounded domain. So you've got this. Okay, so what you do is, I'll just tell you the answer. You can think about it. I think this is the answer. You take the ideal regular octahedron, yeah, I think that's right. And then you cone to one of the faces. This will give you like 1/8 of the regular octahedron. And then you take two of these cones and you stick them together, and this will produce 6 hyperplanes where 3 meet at a right angle, the other 3 meet at a right angle, and then they both meet along an ideal triangle. So you get the 3 cusps. There's 3 cusps here because you can go out this way or this way or this way.
Say that again. You come to one of the faces.
Yeah, you take a regular octahedron, you sit at the center of mass of the octahedron, and then you look at the cone to one of the faces. Each face is triangular,
Okay.
so this gives you 3, like a kind of a little prism. And then you take 2 of these prisms that they look like that, and you take the other one and you put it on the other side, like this. You just stick them together. And this region here, this common boundary is an ideal triangle. And then these angles are
So prism means tetrahedron.
yeah, I mean a tetrahedron, yeah. So it's a tetrahedron where one point is at, say, at the origin, and then the other 3 points are at the boundary. And right. Some members of the audience are excellent at visualizing high-dimensional constructions of these kinds of things, but like yourself. But anyway, this group, this is kind of pretty because if you look at the group of reflections in the faces of a regular octahedron, it's commensurable with the I guess it's the Bianchi group of PSL2 Z adjoin I. So somehow this group is also commensurable with the PSL2 Z adjoin I. Okay, so that's all I wanted to say about polygons. So the idea, the Thurston paper does something like this in, he replaces polygons by polyhedra. Yeah, David?
Do you get a lattice for every n when you do this?
No, absolutely not, absolutely not. I mean, for one thing, like there's no high dimensional discrete reflection groups, that's one problem.
Right.
Yeah, like for a while I tried to think about what you got for the regular 7-gon, but I mean, I never really figured, I don't think so. I don't think these are often discrete. I mean, yeah, that's just something about this construction. This construction will produce lots and lots of, for any, any n, any arrangement of lines, you'll get a real hyperbolic reflection group, but they're rarely going to be discrete. It's just that somehow in the pentagon and hexagon case, or regular hexagon case, you get this kind of beautiful hyperbolic three-manifold or hyperbolic lattice. In general, yeah, you kind of get junk. And this is, so Thurston, so he's going to do, what's coming next is that I'm going to do something like this, but for polyhedra. And the answer is you can do it for any, more or less any combinatorial data for the polyhedron, and you're always going to get something. You're always going to get some kind of complex hyperbolic thing. But very infrequently are you going to get something that comes from a lattice. But when you do, it's a kind of a miracle, and these are the Moss-Alderline lattices. Or Moss-Alderline Thurston lattices.
So like the group depends on the directions you start.
Yes, right.
And so what did you say? So in the case of pentagons, it's always.
Well, okay, so I was just considering pentagons which had this property that the lines focused on sort of the, like there's several, you could say look at the space of all pentagons modulo, well, remove the ones where there are some parallel lines. And so look at the connected components of that space. And what you get depends on which connected component of that space you're in. So I was talking about the pentagons which you can get from the regular pentagon to such a pentagon without going through parallel lines. So call those round. So for round pentagons, you certainly always get a right angled reflection group. But if they look like this, yeah, I don't know what you get. I mean, I think you probably get an elliptic point somewhere, and it's probably going to be bad news.
And what about the hexagon?
I think it's even worse. Yeah, like because you have this cusp, so you change this a little bit, and then you're going to have some kind of elliptic element, and this is probably going to be bad news. I mean, probably going to have infinite order or something. So usually, right. I mean, initially, yeah. I mean, you have some nice angles between these things, but if you perturb it a little bit, you're going to get something bad.
So it's a lattice, it's a lattice when it's regular.
Yeah, that's right.
But
That's right. And the same thing is going to happen in the complex interval case. That for certain special choices, you get nice objects, but usually it's kind of, you get junk. Right. Okay, so the basic object here is you look at flat cone spheres with prescribed cone. So what these objects are is they're topologically they're spheres, and they have a metric. It's not quite a Riemannian metric, but it's just about at all but finitely many points, the thing is isometric to the plane, locally isometric to the plane, and then at these exceptional points, the thing is isometric to a cone. So a cone is just you take a cone in R2, and then you isometrically identify the sides. So an example of this kind of metric is the boundary of a cube with its intrinsic metric. This is kind of a beautiful thing that, I mean, like on a cube, you think it has edges, but if you think of it intrinsically, it's just, even at the edges, it's isometric to a plane. There's a theorem, which I always forget, I think it's due to Alexandrov, that if you have such a thing, it is isometric to the boundary of a convex polyhedron within the intrinsic metric. I mean, Alexandrov's theorem is about some general fact about non-negatively curved metrics on the sphere. But anyway, one kind of interesting thing, which
Positive cone angles.
yeah. That's right. I mean, that's right. I want you could, right. I mean, you could imagine a situation where you took, like a double branch cover of the plane or something. Then you'd have a, negative combinatorial curvature. But I'm only talking about where you have positive. When people who study the translation surface community, these guys study, they study things where the angles of integer multiple of pi, 2 pi. So they're in that world, they're always thinking about negative curvature. But here it's positive curvature. So the idea is that your moduli space is it's a little different than the real, somewhat different than the real setting. Just the moduli space is just all, you fix the cone angles, and you're allowed to vary the metric. So for example, like in the cube, this thing has 8 points, and I'm not going to think on the fly what the angle deficit should add up to 4 pi. I mean, there's an angle deficit where you just take 2 pi and you subtract off the cone angle, so that should add up to 4 pi by the Gaspardine theorem. But anyway, you can take a cube, and you could also double an octagon, and these are in the same moduli space. Yeah. So it's kind of, in a sense, that the set of doubled polygons, so this is a way of seeing part of the real case in the complex case, because you can fix that. If you fix the directions and you start varying the lines and you double it, you'll always stay in the same moduli space. So in a sense, these doubled polygons are like the real points in this moduli space. Okay. Now, so it's not so obvious that this set. I want to explain why. You could make this set of these into a complex, at least locally into a complex vector space. So I want to introduce some coordinates on these. Thurston has some fancy way of describing this in terms of what he calls a cocycle, but I'm just going to do this in a more nuts and bolts kind of way. So the basic fact is that if you have one of these cone manifolds, you can find a spanning tree. Well, okay, one thing you can do is you can triangulate it. There's a fact that, okay, so there's a general fact that you can always triangulate a polygon, you know, and you kind of just cut off a side, and you know, and you keep going until you're done. You can always triangulate a polygon with edges that just connect the vertices. So I want to say the same thing as on a cone surface. You can find a triangulation of the cone surface, which where the edges just connect the cone points, and there are no other vertices. So there's two constructions. One is kind of beautiful, and one you can see how it works. The great construction is like you remove. Okay, I'll say this. Well, I'll just give you the basic construction. Well, the nice thing is that you can remove the vertices. You can take the universal cover, and then you can take what's called the Delaunay triangulation. So that's a canonical construction, but it's a little hard to see that it works.
The what?
Delaunay triangulation.
Delaunay.
Delaunay. Yeah, it's like the set of you look at all the maximal circles, the circles that contain three of the points but don't have any points in their interior, and then you just if you have that you call that a triangle. There's some nice picture in the plane of this where if you have a bunch of points in the plane, you take a ball and you kind of rest it. Imagine these points are like they're kind of all just glued in space, and you take your ball and you just plop it down and it hits three of them, and then you roll it and you just keep rolling it, and this is identifying your triangles. This is sort of a description in the case of the plane. Anyway, another approach is like you pick a spanning tree for this thing. You know, you somehow you take some kind of spanning tree for the thing, and you know, if you take one of minimal length, it'll be embedded, and you cut the thing open along the spanning tree, and let's lie a little bit and say it turns into a polygon. It does, but it may not be embedded. But even if it's not embedded, you know, it turns into an immersed polygon, and then you can just triangulate the immersed polygon by some algorithm like that. Okay, so anyway, I'm going to describe local coordinates on this space based on. So you pick this spanning tree, and then you kind of cut the thing open. Like if you just go around the spanning tree, like so, then what you're left with is a disk. You can just you know, if you like, develop this disk out into the plane or draw it in the plane, and I'll just draw this disk like this. It might be more complicated. I actually have a computer program that will draw these for some cases, so if anyone's curious what they actually look like. But you can then assign a complex number to each edge, because like if this is at the point, you know, z1 and this is z2, then the complex number you can assign is like z1 minus z2. And this number is defined up to multiplication by a unit complex number. And if you don't care about the scaling, it's better to think of these things, you know, like if you multiply this by some other, okay, so you get a bunch of numbers, a bunch of complex numbers, you know, like say E1, E2, etc. And there's some relation between these complex numbers, like because the sides here are identified in pairs, they came from this cut. And so they, in particular, they have the same length, and they're not parallel, but they have the same length. But they're one is like if this one is glued to this one, then there's some unit complex number that tells the rotation, and this unit complex number is determined by the cone angles. So if you were to change the metric a little bit, you get another one of these assignments of complex numbers. But you'd only have to specify half of them, because the other ones you could deduce from what these unit complex numbers are basically determined by like I mean, you make a loop that goes from one side to the other, and you just compute the cone angles that are surrounded by that loop, and then the angle is a complex number of that. So this gives you local coordinates on this space, because what do you need to do? Or conversely, how do you reconstruct one of these things? You pick complex numbers, which, well, they better, when you sum them all up, they better add up to 0, because you want a closed polygon, and that's a linear constraint on a set of complex numbers. And then you also want, when the edges are paired, you want the one to be the suitable complex number of the other one. So you have this little, this is just a little copy of a complex vector space. It's an open set in complex vector space, which describes the set of all nearby structures. So Thurston has a more canonical way of describing this. You could say, like, you lift to the universal, you remove the points, you lift to the universal cover. This gives you, with the developing, you have the holonomy map into C, and then certain elements are mapped to rotations, to multiplications by suitable unit complex numbers. So this, how he calls this, it's a cocycle. And again, it's a vector space, complex vector space of possibilities. Then there's something which I'm not going to do calculation, but you can imagine, like, what happens if you change the spanning tree. And then the answer is these coordinates there'll be a complex linear change of coordinates. So somehow the complex vector space structure is uniquely defined, even though there's different local coordinate systems. Okay, so far so good. Okay, so now the question is, so now there's a function on this space. Now, namely, the area is a function. And then what I want to say is that, just like in the real case, the area turned out to be the diagonal part of a real quadratic form of type n, 1n. The area in this case is going to turn out to be the diagonal part of a Hermitian form of type 1 something, 1 n minus 3 or something. So there's some basic fact which I wrote on my hand. But anyway, if you have a triangle in a plane and its side lengths are z and w, then you take the area is I times I think it's c, maybe it's I over 4 times z bar zw minus e bar. So that's the area of a triangle. Anyway, this thing is a Hermitian. So a Hermitian form is it's exactly like a quadratic form in Cn, except that when you switch the two vectors, the answer is complex conjugated. So your favorite Hermitian form is just so this is your favorite Hermitian form, but possibly maybe it's really you might want to have some pluses and minuses, and then the signature of the form is the number of the number of pluses, comma, the number of minuses. What we're going to get in this case is we're going to get all all minuses and one plus, one plus and all minuses, just like in the real case. Okay, so let me try to convince you that in general, the area is a Hermitian form, and it's pretty straightforward because you have these coordinates on your spanning tree, and then there's also a triangulation that extends the spanning tree, and you can figure out the coordinates. If you have z1 and z2, then this is z1 minus z2 or something. You can label all the edges of your triangulation by the differences in the vertices, and they're all linear functions of the coordinates. And then you can express the area as just the sum of all these triangles. So the area is just the sum of a bunch of things that are Hermitian, yeah. Right. Yeah. So, I mean, you're expressing it as a Hermitian form of these coordinates, and you're always, I mean, yeah, I think that's what I want to say. So yeah. Okay, so let me explain the argument. Why is the signature? Let me explain. I mean, there's two ways to think, like, why is the signature 1n? One thing, if you're very lazy, you could just say, well, if you restrict it to the case of doubled polygons, we already computed that the signature was n1. And if you know the signature of a Hermitian form on a totally real maximal dimensional subspace, then it's not going to change. So that's one way to do it. But you could just the other way to do it is another way to say a very similar thing, which is really just an imitation of the same proof, is that you imagine you have your cone sphere. I'm just drawing a polygon, but you could. One way to think about it is that you could slit the thing. Well, you could slit the thing open along one of the edges, where say you had two nearby points, and then you could glue on a cone. I'm going to try to draw this well. So there's this little cone that you can you literally just slit this open, and you glue on this cone, and you now have a lower, you now have a moduli space with one fewer point, and by induction the signature has type 1 something, and then you can use coordinates where you're just subtracting off like you're subtracting off a positive number, like minus. If you use coordinates where like you maybe you assign a complex number to this edge, then your quadratic form is going to look like minus z minus a constant times z bar times the other stuff. So it's kind of the same argument that you can adapt your coordinates so that one of the vectors you use it tells you how this point relates to one of the cone points that you're kind of coalescing, and then the term it's really two triangles, but when you compute the area, it's just going to be some constant times z bar. So by doing this repeatedly, you diagonalize the quadratic form, and you also see that it's really directly a form of type. Okay, so that means that means that the okay, so let me let me just say a word like this is all set up to say that if you look at the ones of unit area, then in these coordinates it's locally isometric to complex hyperbolic space. So let me just say what CHN is. I mean CHN. The usual way you do it is on C n plus 1 you put the standard conditions. So then you I always mess this up. You either look at the negative vectors or the positive vectors. Then you let say, B equal, set, V such that, you want this to be equal to 1, greater than 0. And then so CHN, I mean, this is a kind of complicated way of saying that if you just set one of the, you can take an affine patch in CPM by just setting one of the coordinates equal to 1. And then when you work out what this set is it's just the open unit ball in CN. And then, the group of complex linear transformations which preserve this form also preserve this positive set B, and they act as biholomorphic maps on the open unit ball, and there's a metric on this ball which makes it a Riemannian metric, and moreover, in fact, it even makes it a Kähler metric. So what a Kähler metric is it's a pointwise varying Hermitian form, so that the real part is a Riemannian metric and the imaginary part is a symplectic form. The reason why this works is that if you look at the set of biholomorphic maps of the unit ball which preserve the origin, they preserve the standard Hermitian form at the origin. And so then you can just use the group to move it around. I don't know. Okay, so then let me give you there's a great proof that this is, at least in 2 dimensions, that this is actually a Kähler metric. So let me, it's worth seeing this neat, quick proof. So you've got this Hermitian form and you take its imaginary part, and that's omega, and you want to see that d omega is equal to 0. Well, this is not related to the rest of the talk, but I just want to throw this in. I like this argument. Okay, so you look at d omega. You look at omega, so this is a 2 form, and you're trying to show that d is equal to 0. So imagine it wasn't equal to 0. Well, you only have to prove it at one point by symmetry. So imagine d omega is non-zero, then this is a non-zero 3 form. But then the Hodge star, which makes sense in a Riemannian metric, is a non-zero 1 form. But then the kernel of a non-zero 1 form would be some hyperplane through the origin. But the symmetry group of this form acts transitively on hyperplanes to the origin, so it couldn't have a kernel. So it has to vanish. So that's a proof that d omega is equal to 0, at least in the case of CH2. It's harder. Anyway, we have some experts here. But
yeah. So you use the symmetry.
yeah, at least for the complex hyperbolic, for the 4-dimensional, 2 complex case, you can just see by symmetry that the thing is Kähler. But in general, you have to work a little more.
Actually, no. I mean, Carton's argument that if you have an invariant form, then it's D0 is exactly that. Just uses the symmetry. I mean, I'm sure it's sort of.
Yeah, no, it's not too bad. But anyway, I just wanted to say this. So anyway, this metric is really nice. It's Riemannian. It has pinched negative sectional curvature. If you normalize it right, it's between like -1 and -4, and then it also is a kind of a model for a Kähler manifold. Okay, if you fix the cone data and then you look at the moduli space, this thing is locally isometric to. I mean, it is. It's a complex hyperbolic manifold. I mean, that's what you get. Every point has local coordinates, and then you're locally isometric to this thing. The point is that when you use these coordinates, what does it mean to scale it? It means you're just multiplying these coordinates by some complex number. So if you mod out by scale, you're modding out by by scaling, and you're exactly getting in complex projective space, and then you have the area thing, which is the diagonal part of a Hermitian form. So this is a kind of a not too far from complete proof that this thing, this moduli space is on the nose. It's a complex hyperbolic manifold. But this is unsatisfying because it's not metrically complete. It's not geodesically complete. So the thing I'm going to explain next is what the compactification is like. And then when you take the compactification, one of two things, you always get something called a complex hyperbolic cone manifold. Although in Thurston's paper, I was not able to figure out what this meant. Thurston says a complex hyperbolic cone manifold is a cone on a cone manifold. A cone manifold is a cone on a cone manifold. So I'm going to say what you actually get. I mean, you actually get something like what I'll call like a fibered, stratified complex hyperbolic manifold, and this is enough to deduce the main theorems. Anyway, you get some kind of thing which is like a cone manifold, whatever that is, and then there are certain situations in which the cone angles are nice, and you actually get a complex hyperbolic orbifold, or in other words, the quotient of the complex hyperbolic space by a lattice. So there's some local conditions on the angle data which will give this to you. So I'm going to try to explain that picture next, like what's the compactification like. Okay, so far so good? I guess, I hope. So there's this basic operation you can do where it's just like in the polygon case. You have one of these cone spheres, and you can slit the thing open along an edge where if there are two close points, and then you can glue in a little. I mean, when you develop this thing out into the plane, what happens is this edge opens up in some way, and maybe it opens up like this, and then what you're gluing in is like something like you take two of these triangles and you stick them, you glue them together, and then you stick them on. But anyway, you just concretely, like in a, if you think of all the other cone points as far away, this thing just looks like a truncated cone. I mean, you're taking a cone and you're just slicing it off, and then you're gluing it together. So you can undo the operation by slicing it and then just making a cone. But what you can do is there's an operation. You can just move these points parallel to themselves. You can just sort of bring them further down in the cone, exactly parallel. And then you can make them coalesce to a single point. So this is exactly like in the, what does this look like in the double of the polygon case? It's like you have a polygon, and all you're doing is you're just taking this side and you're moving it parallel to itself until it goes to here. So when you...
What do you do with restriction area equal to 1 when you think about it? You increase area. You're going to renormalize or?
Yeah, you're going to renormalize. That's right. You're going to
move everything actually. Yes, it's not just concerns a couple of.
Well, it's. I don't want to think of area 1. I just want to think of these things modulo scale.
Okay.
So you do this operation, and then if you're interested in area 1, you're going to have to rescale.
You were interested in area 1?
No, I'm interested in these things mod scale.
Okay.
Yeah, I mean. Yeah, it's convenient just to think of them as, 2 are equivalent if one is.
But then we don't have a metric, right? Then we have conformal structure.
No.
Because you
you have exactly a metric mod scale because you're taking, you get complex hyperbolic space by taking the picture in Cn and modding out by complex multiplication. And when you do that, and when you do the scaling, you're exactly.
If you return to a real case, right, and you write the norm square equal to 1. It's not the same as norm squared equal to 1/2. And if you insist of...
No, well, okay. There are different views of of the real hyperbolic space. One is that it's the surface of vectors of length 1, but it's also, in the Klein model, it's just the projectivization of the positive vectors with respect to this form. And then there's a metric that you can build on this projectivization. You don't have to take a section of this projectivization, right? There's these many models of, you can think of the hyperbolic plane, if you like, as this hyperboloid of one sheet. And then there's this convenient description of the metric as, the restriction of the form.
That's right.
But you can also just say, well, it's just the projectivization of the positive vectors with respect to this form. And then
But when you scale, your metric is scaled, okay, so you cannot induce metric because you get conformal structure. There's no metric.
No, there is. Okay, let me talk about this again. You take the Hermitian form. Right. Okay, all right, okay. Let's go with that. Okay, you get a complex hyperbolic structure mod. You're allowed to scale it, but once you choose this one number, then you're
This I
done.
understand. If you fix to scale, this I understand. If you don't want to fix to scale, I don't see where you get metric.
Well, you get a metric, but you have to choose. How do you build a complex hyperbolic metric? You pick a metric of the origin, which is symmetric under the stabilizer of the origin, and then you just push it around by the group. How many such metrics are there? There's a one-parameter family of such metrics. Once you fix the metric, once you fix a choice of inner product at the origin, the rest of the metric on the symmetric space is determined for you. So you're right. You're not getting a canonical metric. You're getting a canonical.
That's it.
But you're getting a canonical metric up to a choice of a single number. And for the purposes of analysis of everything, it doesn't matter where, it's like I'm saying, you're, right. You don't have to take things of unit area, although if you, I'm
You
not.
have the fixed area. You can take it to be equal area 1/2, but you cannot all
No, you don't fix it. You just consider these objects modulo scale. This is the same way that this is what complex hyperbolic space is. It's the,
When you look to homogeneous space and you say you take something at one point, you just do group action, and then you fix it at one point, you choose some scale.
fine.
At that point,
Yeah.
1/2 or 1, doesn't matter.
You choose some scale once and for all, but the isometries that the complex linear maps that act on the ambient space, they will be isometries in any of these metrics. They're not conformal transformations. There's two things they could be. One is they could be a conformal transformation of any metric you choose, where the conformal factor varies with the isometry. That would be bad. But whatever scale you pick, these maps are all isometries.
Yes.
So fine. But what do you mean by the plane anyway? You and I pick our coordinate systems for the plane, and every object is considered up to isomorphism. There's some different versions of the complex hyperbolic space are. You might say they're not isometric, but they're isometric. There's a map between them which changes distances by some one number at every point. So I'm saying, so what? For the purposes of this operation of coalescing the points, I'm just considering these spheres mod scale, and so I'm just.
That will be important when you say geodesic completeness, right? Talk about metric. So
It's a computation. Okay, right. No, it's
otherwise.
okay. All right. So no, okay. You have to compute that this operation is complete, and so
If you just like to say that, look, in finite time I arrive to boundary, it's
Right.
complete. No, that's not quite the same because you constantly change the metric.
no, you have the scale fixed. Once you fix the scale, it's the whole metric is defined up to a single number. So if you picked 5 times, if your metric was 5 times my metric, it would take 5 times as long. But the fact that it occurs in finite time is independent of this one numerical choice that we're agreeing on. So, I'm not going to do the calculation. You have to check that in this metric, you just have to write it in local coordinates and see that when you integrate the suitable path, that, it's just a finite integral. It's a calculation, and, you don't need to normalize it. You just have to, express the metric in the local coordinates you use. All you're doing really is, you have this number, you pick one of your coordinates so that, you have this number z, and then you're moving in it, and, most of the coordinates are not changing at all. You're just kind of changing this single number z, and then you just have to write down in these coordinates how the thing is changing. It doesn't matter if you rescale it as unit area. You're only making a bounded change in the area. Okay, anyway, I'm not actually going to do that calculation. But there is a calculation to do, and you're right, it's not completely obvious that in this metric. But when you write down the coordinates, you can see that all you're doing is you're just moving one coordinate in Cn, and you just have to restrict the form to that path, and it's only a finite path, and you're staying away from the boundary, and so it's going to be finite. That's sort of the idea, I guess. Yeah. So anyway, there's a calculation, but if you can just see what you're just changing one number. You're just moving along this more or less a straight line in Cn, and the line isn't going near the zero set of the form, and so when you integrate the form over the line, you get a finite number. I don't know. That's the idea. Okay. Is that you?
Okay.
Okay. This is kind of analogous to what happens like for like the moduli space of curves or something, like in the Day-Peterson metric. If you pinch a curve, and then you can reach the boundary of the moduli space, or the type-Miller space for that matter. And then what you get in the type-Miller space picture is somehow there's lower dimensional strata, which are like moduli of kind of degenerated Riemann surfaces where say like one curve is pinched or more than one curve is pinched. And so what you see in the boundary, if you take Day-Peterson metric on type-Miller space, it's incomplete, and then if you complete it, what you're doing is you're adding a bunch of lower dimensional copies. And so I want to say that the same thing is going on here, because there's this operation, like how do you get the strata? Basically, you pick any collection of cone points where the sum is less than 2 pi, and it's then possible. It's hard to draw with more than 2, but they're kind of, you can kind of think of collapsing them 2 at a time, but you can collapse them to a point, and this is reaching some stratum. And what you're getting is a sphere where it's another moduli space where you just have different cone data. So for example, like if the cone deficit was alpha and beta, and then there's some other ones up here, after you collapse it, you'd have all the same data up here, but down here you'd have alpha plus beta. Because the whole thing is going to be equal to the sum of all these numbers is going to be 4 pi. So the idea is that when you do this, if you complete this, that what the completion is you're allowed to coalesce any number of points where the angle sum is less than pi, so that you really do focus in a cone. And for each one of these partitions like this, or for each way of getting angles of sum of less than 2 pi, you get some stratum in the completion. And these, just like in type-Miller space, these strata are nested. Like if you condense 2 at a time, you get a codimension 2 stratum, because the complex dimension changes by 1. And then if you coalesce more, you get sort of lower dimensional strata. So the way if you've not thought about these stratified spaces, a good picture to have in mind is just something like the boundary of a cube, where like the inside is the top dimensional strata, and then the faces are the next strata, and then the edges are the next strata, and then the points are the strata after that. but this is the same kind of picture, except that the strata are, it's always codimension 2. Or even codimension. Okay. So then there's more work. Okay, so I just to give you, just trying to give an overview, but these strata are just, the metric extends to the strata, and it's the same local coordinates, and the strata are also lower dimensional copies of complex hyperbolic space of lower dimensions. And they're basically, the strata are basically, at least locally, they're given by linear subspaces of Cn, and so they're geodesically embedded. So what you get when you take the completion is it's a union of complex hyperbolic manifolds, which you can, it's a stratified complex hyperbolic manifold. But then there's more, because there's a kind of, let me just explain this in the codimension 2 case, but it's also has the structure of a kind of a fiber bundle, because like just, this is the only picture I really understand. But the idea is that like, there's, okay, so like what's the base space? So the base space is you look at, you add the cone, and then you look at the moduli space of the simpler manifold, and there's a disk's worth of structures that go to that same point in the base space, because what you can do is you can take these 2 points, and well, firstly you can just kind of drop them down like this, but you can also yeah, I guess you can kind of rotate one around with respect to the other. So like the way I picture this is like you cut this thing open, and then you take this kind of slit picture, and then you kind of squeeze it like on the side, and it goes out like this, and then you re-glue the cone back in. You could almost do this with a piece of paper, like, I mean, you have this kind of slit, and then you cut it open, and then you just kind of re-glue it like this. But you have an angle that can, or just put another way, if you just take this number z and you can just multiply, you can just vary this z continuously, and this will give you another structure. The picture, so if you're near if you're in the codimension 2 stratum, then what you see is metrically what you see is, I'm going to lie and then fix it. What you see is a disk bundle over, you have 2-dimensional disks, and they're sitting over this this base space of codimension 1. And then you could also do this in with higher dimensional strata. Well, this is, in general, if you coalesce like 3 points, then your base space is just all the fibers are all the things where you get the same structure on the coalesced space, and then the fibers, I just want to say they're balls of the appropriate dimension, but that's a lie. So I want to say more precisely what happens. At least in codimension 2, what happens is like when you work out these coordinates, this z, okay, this is a pain to prove, but I'm just going to tell you the idea. When you start varying z around, if these angles, z will change by less than 2 pi, and you'll get back to the original thing, because these points are kind of rotating around a cone, and it doesn't take them as long to get around. So somehow what the real picture is it's like a complex hyperbolic disk cone. So you take the complex hyperbolic plane and you cut out two geodesics going from the origin, and you glue this together. This is a complex hyperbolic cone. And so when you work out the metric and local coordinates, what you see is like it's not exactly a disk bundle. It's a bundle of cone disks of complex of just real hyperbolic. And so the what's going on is that you have this bundle of disks with cone points, and the cone points all line up, and they give the codimension 2 strata. So what the codimension 2 strata looks like is like you have one lower dimensional complex hyperbolic space, and then going around in the normal direction, you have these disks, but the cone angle is a function of, like, the cone angle is like 2 pi minus alpha plus beta or something like that. Okay, so let me just summarize. Are people dying, or is it's okay?
Okay.
Okay, so firstly, like, there are these special coordinates, and you compute the area in these coordinates, and then when you projectivize, you after you choose a canonical scale, you get that this thing is a complex hyperbolic manifold. But this coalescing operation, you can compute or reason in some way that it's a finite distance in this metric in any of the, whatever scale you pick, and so it's not complete. And then when you complete it, all the completions just come from taking collections of these angles which sum up to the deficit's less than pi, or 2 pi, and you coalesce, and this gives you the lower dimensional strata, and they're all there's kind of a poset of these angles, and then the strata are organized in the same way as this poset is organized. If you take sub-collections of a collection, then the stratum you're going to get is going to contain what you get for the whole collection.
Do you always need to geodesically complete them, or there are some cases where, of some configurations, where they actually complete?
There are some trivial cases where they're complete, like maybe.
Like cubes?
Well, no. As long as you can find two angles where the sum is less than 2 pi, it's incomplete. So you have to give me a list of numbers that sum up to 4 pi, no two of which sum up to anything less than 2 pi. So there's not that many choices for this. I mean, like a square, like the double, I guess like the double of a square would be an example. And what do you get in that case? The modular surface, basically, or something. I mean, in that case, so sometimes the space is compact and sometimes it's not. When it's non-compact when you can find a collection of angles which sum up to exactly 2 pi, because then you can kind of, when this coalescing operation won't work, you'll get
Incomplete, not complete.
Well, I mean the quotient will be unbounded. You can get unbounded completions, because if you have angles, if you can partition the angles into like in the regular hexagon case, in the real case, if you partition the angles into where the sum is 2 pi, then you can just kind of, you can take your structure and you can insert a cylinder, and that makes it longer and longer. Right, I mean, your cone manifold kind of looks like this. And then you can just cut it like this, and then you can add a bigger cylinder. You can keep adding more and more, and this is, like you're going, out the end. You can still compute that it has finite volume. These kind of look like cusp ends in a complex hyperbolic manifold. So in any case, these things have finite volume, but it's very hard to get them to be complete. They're just a few cases. Okay. So the beautiful thing is that when alpha plus beta, so some things are nice. Like, it could happen that this angle is 2 pi over an integer. That could happen. like you look at, yeah, I guess like, well, you're doing the deficit, so like alpha plus beta could be, 2 pi over n. It-
Keep mixing me up between angle and.
So these are
angle
deficits. So what I'm labeling these numbers are the angle deficits. So a point that was not a cone point would be labeled by a 0.
So wouldn't it be alpha plus beta is 2 pi minus 2 pi over?
Oh,
Okay, never mind.
no, let's see. So this is, okay, so this is alpha plus beta. And yeah, this is the thing you want to be a multiple of pi. Yeah, so 2 pi minus alpha plus beta should be 2 pi. Yeah. Right. This is 2 pi minus alpha plus beta. So when you put it together. Also, if the cone points have the same, there are some subtleties here which I'm ignoring. If the cone angles are the same, then when you go halfway around, you're already sort of at the same story. So, it's a slightly different condition if these are the same. And the condition depends on whether you think of these things as being labeled or unlabeled. So it's easiest for the analysis just to think about them as everything is labeled. And then when you get into the fine points, you can forget the labeling and you get some slightly different space. But I'm just ignoring these fine points, plus I can't remember them exactly. Okay, well, anyway. So the good case is when this angle is it's 2 pi over an integer. And then the intuition is that if you start developing this thing out into the complex hyperbolic plane, it's going to kind of go around this codimension 2 thing, and it's going to come back after a finite number of steps and close up. And so if you look at the holonomy of this structure, it has a chance of being a lattice. And then Thurston has this theorem. He quotes 2 theorems. How they're proved, I don't know. He says that if he calls these codimension 2 conditions, if you have this property that after a finite number of steps it closes up, and he calls these codimension 2 conditions, the upshot is that if you have this, then the space is isometric to the quotient of the complex hyperbolic space by lattice. So let me try to give you some rough idea of the proof. The proof I gave in my notes. I don't know what Thurston does. Thurston quotes this thing called the orbifold universal cover. He quotes 2 theorems. Like he says that if you have these codimension 2 conditions, then all higher codimension conditions are just automatically work. And then if you have such a thing, it is a Ball quotient. He has this thing called the orbifold universal cover theorem. But let me just sort of explain the idea. So you have this stratified space. I'll just call it M or something. And you remove all the singular strata. And then you take the universal cover of that. So this is kind of a monster. So this is like the universal cover of M minus kind of this sing is the sing, this lower determinant. And then there's there's a holonomy map from M gamma into CHN. This is just the developing map. Okay, you just develop this thing out. And then there's a subgroup of trivial holonomy. So for example, like if you have this orbifold, this codimension 2 condition, there like this element that goes around the singular set 5 times, it's going to be the identity. So there's a subgroup of the holonomy group, of the fundamental group of this monster, which develops, which has trivial image. So there's like the kernel of the holonomy map. So intuitively, this is like generated by things that go some finite number of times around the codimension 2 singular set, and then you take M tilde mod the kernel of the holonomy, and then the claim is that this is isomorphic to CH atom. And then the way you get the ball quotient is you just quotient out this guy by the rest of the holonomy. So the reason why this works, here's the intuition. You can, the codimension 2 sets are removable because you're going around like 5 times and then you're just, you just set it up so that these things are removable. All you're left is, once you put those back in, you're left with the filled in thing just has codimension 3 singular sets. But the result is, if you take out something of codimension 3, it's simply connected. So the development map doesn't depend on which way you go, and so everything else is removable as well. So that's sort of the sketch of the proof that this thing is really a ball quotient. You remove the singular set, you take the universal cover, you mod out by the kernel of the holonomy map, and then you prove that this is isometric to complex upper box space just by, yeah, sorry. You take this and then you complete it. Yeah. Right. Or you could say that another way to say it is that if you don't do the completion, it's just a complement of a bunch of totally geodesic subspaces of various dimensions. Okay, okay, I have about 7 or 8 minutes. I just want to say I didn't quite get to, there's one more punchline in this paper. So like, for example, when do these, you can check that, like, if you take the regular icosahedron, for example, then that moduli space works. And like the ones you know and love, like the moduli space of the regular octahedron and so on, these things all have this codimension 2 condition. So they all give rise to complex curvature lattices. So Thurston, it's sort of a combinatorial problem to write down all the angles and all the data and just figure out which ones give rise to these conditions. And when you do, you exactly reproduce, you get a bunch of lattices, namely these quotients, and those are the Deligne-Mostel lattices. And then I wanted to say one more thing. Thurston, so there's a nice special case where Thurston used this technology to talk about triangulations of the sphere where the maximum degree of the triangulation was at most 6. So if you have a triangulation of the sphere like that, for example, the icosahedron or something else, I think these things are called fullerenes. But if you have one, you can just make all the triangles equilateral, and you can glue them together, and this gives you one of these cone structures. So every possible triangulation of the sphere with max degree 6 is a point in, well, technically it's a point, it's not exactly a point in this moduli space because the scale is important. So it's sort of like a point in a, it's like like a circle bundle over the, something like this, like a bundle over this moduli space. Because you're also concerned about the scale. But anyway, what happens when you work out the what you can do is you fix the list of degrees that are less than 6. Like the classic one is, the classic case is there's 12 points of degree 5 and everything else has degree 6. Another case is like there's 6 points of degree 4 and the rest are degree 6. Anyway, if you fix the deficit data again, then all of these points arise in the same, they're connected to the same one in the same moduli space. And in those, what happens in that moduli space? Well, when you work out the coordinates, you take the spanning tree. Well, there's the Eisenstein integers. These are like z adjoining cube root of unity. And when you plot the Eisenstein integers in the plane, they make regular, the tiling by regular triangles. And so when you write out, you take the spanning tree, you develop this thing out, and as long as you rotate it the right way, all of your coordinates lie in the Eisenstein lattice, and all of the transformations you get. The whole structure, all the entries in any matrix you might see, in this case, in all these cases, the codimension 2 condition is satisfied because you can just see that everything is like, 2 pi over 3 or whatever. So these cases all work. They're all orbifolds, and all the matrices, everything in sight is just defined over the Eisenstein integers. So in fact, in this case, you get these when you just work out the matrix group, you actually get you get a lattice in PU, whatever it is, 1, 9, I guess, in the most general case, where the lattice is defined over the Eisenstein integers. It's like PU21 of the Eisenstein integers, and the quadratic form is defined over the Eisenstein integers. The one where there's 12 points of degree 5 is like the master one, because the other ones are all, in terms of the moduli spaces, all the other ones are just contained in boundary strata. So there's this one lattice in C19, and all of the lattice acts on C19, and what the triangulations correspond to are positive vectors. And then when you work, because it's the area form, the length of the vector in the right quadratic Hermitian form is just the number of triangles. And so the triangulations are in one-to-one correspondence with orbits of, there's some lattice in gamma C19. And there's a bijection between the orbits of gamma orbits of positive vectors and these triangulations. So it's a kind of complete classification. I will say, Karen's son, Peter Smiley, recently he was able to basically, I'll lie a little bit, and you just count the number of all these triangulations with max degree 6, and you count all the ones that have exactly n triangles, and but you don't quite count them. This is you count them, but you weight them. For the case where there's 12 things of degree 5, you just weight them with 1. But if there's these kind of more degenerate ones, there's some different number you associate. But the total number, it turns out to be some fraction, just some fixed fraction times total number equals some fraction times summation. The number of triangulations of n triangles is like the sum of d divides n, d to the 9th power. So they were able to use this technology to actually get an exact count, number of triangles of positive combinatorial curvature. And it really uses the Thurston theory. It looks at the number theory of this, in this complex hyperbolic space. And so anyway, there's a recent advance on this stuff. So that's the final picture. There's this one lattice on C19, and there's this Hermitian form, and maybe the square length of the vector is the number of triangles, and the triangulations are in bijection with the orbits of this lattice of the positive vectors. So that's the vision of triangulations of non-negative combinatorial curvature.
So it's d to the 9.
Yeah, this is some kind of
12 minus 3, or something like that.
But are these guys coefficients, full coefficients of Einstein series?
probably. Yeah. There's some. It's a number theory. I don't want to pretend to understand this paper.
Right?
Yeah. But there's modular forms in this business, in this count, and
Okay.
and this is right. These are coefficients. Yeah, these are coefficients of
That
Eisenstein
sounds
series.
like a Zevie mass formula somehow. Because you were saying you have to weight the.
Yeah, you have to.
Yeah.
Okay. Well, you. Yeah, in 5 minutes you know more about this than I do. But yeah, these are indeed coefficients of Eisenstein series. But there's some special form that he considers in this complex hyperbolic manifold, and you integrate it, and somehow you make a count, and
It's really connect.
and this is what you get.
Also in the technologies connect.
Yes. Yeah. So anyway, again, I lectured on this. Actually, David was in the audience. I lectured on this many years ago at the University of Chicago, and I didn't really understand the paper, but the audience was tolerant. And then a few years ago, I decided to lecture on this again, and I just could not understand what Thurston wrote, so I wrote these notes that are on my website. People can, and they're on the archive too, if people are interested. There's some of them are, yeah, anyway, it's complete in the sense that all the details are, the main details are, and you know, and then, but it took me about a month to lecture on this, so I sort of compressed all this into about a month, but I hope it still makes some sense. I gave you a feel for the theory.
But this list they have of 94 orbifolds.
Yeah, right.
Some of them correspond to the Eisenstein, to the pi/3 angles, right? Is that-
Yeah, and some of them are unrelated, yeah. Right, you can
But
also.
most of them are, I
Well,
mean, like the,
you mean
if it's an
what percentage?
icosahedron, a cube, or a tetrahedron, that those are only certain, like.
Yeah, there's other things you could do.
You can have 1/8 and things like that.
Yeah.
too.
Yeah, there's other possibilities. That's right, but there aren't that many because, you know, once you, yeah, I mean, I guess like once you have a lot of angles, I mean, you have to pick every pair and check this
Yeah,
condition.
no, I remember looking at one of the Deline Mostow or Mostow, and they'd have some, they'd have an arithmetic written next to it, and some they'd say
Right.
non-arithmetic. Arithmetic meant they were the ones that came from.
Oh, yeah, that's right. So that's right, that's a good point. I mean, so, yeah, so I said that a little wrong. I think that they were excited because there's this problem which John Parker lectured on a little bit, that you know, in all non-positively curved symmetric spaces, I guess, let's just say, or let's just say for rank one, like for quaternionic hyperbolic space and real hyperbolic space and the Cayley plane, they know in real hyperbolic space there was this construction of Gromov and Piatetsky-Shapiro which gave non-arithmetic lattices in all dimensions. And then there's this rigidity, there's this result where in quaternionic hyperbolic space and Cayley plane in any higher rank symmetric space like SLN R mod SLN, there are none. They're all arithmetic. And then in complex hyperbolic space it's still open. It's kind of famous open question. And so Mostow and Deline found these few, and Thurston kind of found the same ones. And I remember talking to Mostow about this one time, and Mostow said, "Yep, son, we got them all." And I was trying to ask him, like, I asked Mostow if he thought he got all the complex hyperbolic
Said he
lattices.
missed them, yeah.
No, he said no. At the time I asked him, this was like, you know.
No, that's what Mostow said, but in fact, my memory is that in fact, before 1988 or something, Thurston had this, he was saying something about this result. He started saying, oh, there's this very interesting thing about complex hyperbolic orbifolds. This was back like in 1979 or 80. And he said, yeah, and I listed them on a computer and they counted them wrong. They have like 93 and the answer was 95 or something.
Okay, but that's different. All right, that's a little, that may be true, but they missed some that are not on the list. Even John Parker and his collaborators found, you know, like, they tripled the number of non-arithmetic lattices. But I just remember it was funny, Mostow was saying to me, like, yep, we got them, you know. There aren't any others. He was pretty confident that they had them all. But anyway, anyway, one significance of this is just that it it's well, I mean, it's a geometric way of seeing this construction of Mostow and Deline, which, well, it depends on your background, but I think it's harder to understand. I mean, the Mostow-Deline construction.
Yeah, well, I mean, Mostow's original thing was groups
Concrete.
Generated by
Yeah, they had these,
complexes.
it was just, he constructed these concrete fundamental domains or something, right?
Maybe, yeah,
Or
that's what he said he
some-
was doing, yeah.
But yeah, I mean, although I think he made some mistakes actually. Like he didn't, I mean, it's since been, like Parker and company found much simpler fundamental domains for all of them, and plus, you know, twice as many more or something. But I think in 1980, like trying to prove these things with a computer is pretty daunting. Right, I mean, a lot of these fundamental domains, according to these guys, like they had lots of faces, and some of them were quite small, and you know, and so it's easy to miss it numerically. Right?
Yeah, I tried to give a course on that once in the early 80s, and it was, and I finally decided his fundamental domains are not convex, right? Because
Well, right, yeah, you don't, that's,
Equidistant systems aren't convex, and then he started talking about faces being digons and things like that. So-
no, that's right, that's why complex hyperbolic space is so hard. Like, well, look, for perspective, like, the isoperimetric inequality is not known in complex hyperbolic plane. It's not known that the balls minimize the surface area to volume ratio. So that's pretty bad, right? Like, people don't know that much about the symmetric space. I mean, you know, you might, I mean, that's, I don't know if that's any easier, but no one's, I think like whenever you have like a codimension one reflection, whenever you have isometries with codimension one fixed point sets, the isoperimetric inequality is known. There's some symmetrization argument that works. But somehow, so complex hyperbolic space, yeah, it doesn't, I mean, anyway, but, okay, well, anyway, maybe that's it's also a really neat kind of thing. Yeah. All right, well.
Oh, that was